Thanks. I'll begin with a word of prayer. Heavenly Father, we thank you for just another day to meet together and to study your creation. We thank you for the truth that you allow us to understand in mathematics, and just pray that you be glorified in what we do this day, Lord. In your name I pray. Amen. Okay, so no, you should not be able to do the homework yet. Okay, we're not quite there. I mean, there may be parts of it you can understand. Depends. If you've had physics, you probably can do it. Parts of it. But we're going to pick up today again on the problem of dot products. And so, among other things, we'll gain further insight into the unit vector concept I introduced yesterday, all right? So, what's a dot product? So, first of all, I'll just give you the definition. So, if we have a vector v, which is equal to, say, v1, v2, vn, all right? You can rewrite that a couple different ways. You could write this as the sum, I equals 1 to n, of v sub I, x hat sub I. All right? So this is just the n-dimensional version of what we did yesterday. So like here, x hat 1 is 1, 0, 0, x2 hat 0, 1, 0s all the way down. And then finally, you keep going and going. Eventually, you get to the nth unit vector along the nth Cartesian coordinate direction. Oops, 1. All right. So basically, you can build an n-dimensional vector using these things. All right. And then the scalars, the v sub i's, v sub 1, 2, 3, so forth and so on. These are the scalar components of the vector. All right. Likewise, we have w. All right. So given this setup, we define the dot product. V dot w, all right? Here's the formula for it. It's v1 w1 plus v2 w2 dot, 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 all the way to vn wn. So this is the dot product of v and w. Now, that formula is fine. In fact, that's very useful for calculating specific numerical examples, but it's nice for the purposes of theory, which we're going to do a fair amount of today, to have a more convenient sort of compact expression for this. And so there, the sigma notation helps us out a lot. This is entirely the same as writing the sum, I equals 1 to n, of v sub I, w sub I. Okay? Now, I haven't really used the x hats just yet, but I just wanted to remind you that they're there. Any questions so far? So let me show you a couple of examples. Like, for the most part, we're working in 2 or 3 dimensions, all right? But, so here, example 1. Suppose we have v equals to 1, 2, and w equals to 3, 4. Let's calculate the dot product of v and w. So what we do is we do 1 times 3 plus 2 times 4. What do we get? 11. All right, good. I know it's early, but I think you can do that, right? Now leave yourself a little space. We'll add a little bit more detail to this here after we've developed a few more concepts, all right? Leave yourself a little room to write more here. Example 2. I think I can do example 2 here, actually. Save myself some room. Suppose we've got, and I'll change the letters on you. Suppose we've got vector A equals to 1, 0, 1. And suppose we've got the vector b equals to minus 1, 1, 1. All right, let's calculate the dot product of a and b. A dot b equals to what? 0. Very good. Now, the reason he knows that is we've got 1 times minus 1 plus 0 times 1 plus 1 times 1, which is minus 1 plus 1, which indeed is 0. So I think can you guys do dot products? Oh, there's no need to follow me around. Just you can focus on the board. Where I am is completely uninteresting. I know, like in other things that are more exciting, like stories about our life, we have to follow the person talking. But here, these are the main characters. Focus on them. So what are the properties of dot products? So this is my proposition 1.1.12. I'm going to write it down. It's important for us to know these things. So I'll prove a couple. First of all, it's commutative. A dot B is equal to B dot A. There's actually something even more sort of primordial that we might notice. What is a dot product? If I take A dot B, what is it? Right, it's a scalar quantity. So that's like one of the first and most important observations you make, is that the dot product takes in two vectors, right? But its output is a scalar. Over the next half-hour class or so, we'll hopefully come to an understanding of what that scalar means. All right? It's going to take us a little while, but we'll get there. I'll even show you some physical applications while we're at it. Let's see here. A plus B. So these are the left and right distributive properties of the dot product. So basically, the dot product behaves a lot like ordinary multiplication, doesn't it? You can pull scalars out. So if think about like a scalar multiple. So B is just a number. I can pull it out. Right? And you can also pull it out of the front. So like if I had C times A, this one won't seem like anything to you guys, but it's also actually a thing. Okay, I mean, so you can pull the scalar out of either input to the dot product. All right. 5 is very exciting, although you may not appreciate why yet. A dot A is greater than or equal to 0. And 6, so this is the dot product of a vector with itself is non-negative. And finally, we have the no null vector property. A dot A equals to 0 is true only if A is in fact the 0 vector. No null vectors. If you study generalizations of dot products, for example, like the Minkowski product in space-time, there are vectors which are 0 and yet have a Minkowski inner product of 0. In fact, these are light rays. That doesn't happen here. This is more, nice, simple Euclidean geometry, as it's known. So what do you guys want to start with? Let's start with number 1. All right. So what's the proof of this look like? I'll put the proof right here, if you don't mind. So A dot B is the sum, I equals 1 to n, of AI BI, right? But consider this. What is AI and BI? These are just real numbers, right? Real numbers commute. So I can switch the order of BI and AI. And then this, of course, is B dot A. So the dot product is commutative. I'll do one more of these. How about this one? This one's kind of exciting. A plus B dot C. How is that? That's going to be equal to the sum. And so here we're going to have to use something we defined yesterday. I'll do it in stages here. So we have the vector A plus B is a vector, right? We take the ith component of that, and we multiply it by the ith component of C. What is the ith component of A plus B? What did we define yesterday?
The ith component of A plus the ith component.
Right, so this is actually AI plus BI, ci, right? But then these are real numbers, so we can distribute. So we can write sum aici plus bici. So again, here is, just to give you the reasoning, definition of dot product. This one is definition of vector addition. This one here is just a property of real numbers. My next step is to write, this is the sum I equals 1 to n of aici plus the sum I equals 1 to n bici. This is just a property of finite sums. The sum of sums is the sum of sums. Sorry. Property of finite sums, though. And then this is exactly a dot c plus b dot c. And there you go. That's why this is true. This proof that I showed you works just as well in 2 or 1 dimensions as it does in 3 or 4 or 5 or 6 or whatever. Okay. So when I can say something about n dimensions with virtually no extra work, I'll do so in here, right? But yeah.
Is that syntax saying a equals 0 general? Like you can say, you can use any number in the place of a vector that has that number as all its components.
To say this, yeah, the zero is a degenerate thing, although not degenerate in the sense of current society. Degenerate in the sense of, oh, I'm sorry. Am I allowed to say that? Are we allowed to make judgments on society these days? I don't know. Judge not lest ye be judged.
Oh, I mean,
I don't know.
so I think it's okay.
We're at liberty, so it's okay. Okay, yeah, I don't know. But of course, we're all sinners. But perfunctory statement. But no. So 0 is a curious thing, right? We use that symbol 0 for the 0 vector, the 0 matrix, the 0 number, the 0 function. Yeah.
Would it make more sense if you put a little vector?
We don't. I don't want to. I mean, you could if you wanted to. I will tell you, there exist those creatures called physicists, some of which who write in textbooks, you don't put a vector over the 0 vector because it doesn't have a direction.
Okay.
But I don't read that much into notation. So you want to put it there, you put it there.
Okay.
It's just, I mean,
If it does have a direction, it's going to be defined.
it has all directions. That's the thing. Anyway, or yeah. Okay, so let's get into this though. What is the formula for A dot A? So, I can write it in the summation notation. Although that doesn't really help us much here, so I'm just doing it for the sake of, whatever. But what this really is what? Is A1 squared plus A2 squared, plus AN squared, right? So, is it clear that that's greater than or equal to 0? You have the sum of squares of real numbers. Worst case scenario, they're all 0, right? That's how you get 0. But otherwise, it's positive. Oops, we accidentally proved 5 and 6. Sorry. But it really is just this silly formula, right? The only way you can get a sum of squares to be 0 is if you have exactly the sum of 0 squared plus 0 squared plus 0 squared plus 0 squared. If you want to see me prove that, you've come to the wrong class. Okay. So, great. These are the basic sort of arithmetic properties of the dot product. Now let's talk about inequalities for the dot product. But first, to do that, I need to make an identification, guys. And you can already kind of see it from here. What is this? What is this thing I just wrote here? We defined this last time, actually. Yeah.
It's the square of the norm of the vector.
Exactly. Yeah, exactly. This is the length of A squared. So the dot product of the vector with itself gives us the length of the vector squared. So in our other notation, we said that was a squared, right? And that's like magnitude direction notation we introduced yesterday. Okay. So what this means then, so here's like a fundamental observation. Let me just write that down again, because this is important. The length of a vector v is equal to the square root of the dot product of the vector with itself. But usually we use the length of v squared is equal to v dot v for proofs and derivations. Lots of homework problems are based on this trick, all right? This isn't exactly a homework problem, but it's something important. So let me tell you some of the properties here. So this is proposition 1.1.13 in my notes. So here's the rundown here. First of all, if we have the norm of c times the vector a, I mentioned this last class, but I'll prove it here for in just a second. If I have c times the vector a, constant, a scalar multiple of a, that is equal to the absolute value of c, right? The magnitude of c as a real number, times the magnitude of a. Right. 2, we have a triangle inequality. And that says that the norm of a plus b is less than or equal to the norm of a plus the norm of b. All right? There's also something called the Cauchy-Schwarz inequality. And that says that the absolute value of a dot product. This one's really important because this is going to allow us to define angle measure here before too long. The absolute value of the dot product of a and b is less than or equal to the norm of a times the norm of b. This is the Cauchy-Schwarz inequality. All right. So there's also a 4 and 5 here, but I won't. They're already kind of immediate from the other one, so I'm just going to focus on these guys. Oh, fine. I'll regret it later if I don't write it. Welcome to my world. Greater than or equal to 0. You know, I love my job. In literally any other circumstance in life, if you sit people down in a room and try to talk to them about math for an hour, they'll think you're crazy. Like, every pastor will politely ask you what your job is. But they're not going to listen more than about 2 minutes. And most of the conversation will be about how they took trigonometry in high school or something. Because they think that that's math. There's a lot more math past trigonometry. A lot. Okay, anyway, you guys, we up to, all right, so let me show you how to prove these things. So this one, right? We're going to use what I just wrote up here, right? So if you look at the magnitude of CA, right? Let's look at this. Good grief. CA, A is the vector, squared is what? This is CA dot CA. But what did we say about the scalar product? You can pull the scalar product out of the dot product, right? I haven't proved that, but you could with arguments similar to the ones I have over there, right? So this is c squared times a dot a, but what's a dot a? Right. So do you guys know how to define the all right, so sorry, I'm words. The square root of the magnitude of CA squared is equal to the square root of c squared magnitude of a squared, right? Take the square root of both sides. What is the square root of the square of a real number? Well, it's the absolute value of the real number. In this case, it cancels because it's clear that the norm is positive, right? Or non-negative. So this is just the magnitude of CA because we know that the norm is non-negative. I mean, like this observation is easy to see just from, I mean, the definition of the norm is the square root of the sums of the squares of the components. So like 4 is immediately obvious from the definition of norm. So this is that. And over here, we have the square root of C squared times the square root of the norm of A squared, right? Which, by the way, is just absolute value of C times the norm of A. By the way, the norm of a real number is just the absolute value. All right, so like norm is a generalization of absolute value. It measures how far the vector is from the origin, just like absolute value measures how far the number is from 0 on the number line. Same idea.
So just like the triangle inequality for absolute values, it's just what you get when you collapse that triangle inequality to one.
Oh, right. Yeah, in one dimensions, this becomes the garden variety triangle inequality for the reals. Yep, which people may or may not be familiar with, but okay. So how do you prove 2? I'll do it over here. I think you guys, even if I didn't tell you these things, you might have guessed these, right? It's just kind of like, these are natural. These guys over here, I think, are a little bit less, you know. I think it would have taken me, personally, a lot longer to discover these than these. Let's see, where was I? Okay, so let's look at the triangle inequality. So we'll look at the norm of A plus B. And we're going to use our square trick again, right? Because squaring it does what? We just take the dot product of the vector with itself, right? Then we distribute using the things I just erased. So this is A dot A plus B dot A plus A dot B plus B dot B. All right? And so what's that? Yeah. Oh, my notes are out of order. So logically, we're going to have to take a, sorry about this, folks. We're going to have to take a logical loan from number 3 to do number 2. So like, in order to do number 2, I need number 3. Sorry, but I put these in this order. Like, for me, pedagogically, it's easier to understand this than that. Like, to me, this is kind of like a harder thing. But it turns out I need to know 3 in order to prove 2. Let me show you why. So what do we have? This is the norm of A squared, right? And here we have 2A dot B, right? So what does the Cauchy-Schwarz inequality tell us? It tells us that this is less than or equal to, I'm getting very tired of this notation, so if you don't mind, I'm going to use A squared plus 2. Oh, fine. I've come this far. So many stupid double bars. Why didn't I get rid of them earlier? I regret my life. All right. So I'm just using the Cauchy-Schwarz inequality to get from here to here, right? But now you see you've got, what is this? This is exactly equal to what? Can you see it?
And you can do that stuff because any number is less than or equal to its absolute value, right?
Oh, right, yeah. So fair enough. There's a middle. You have found my I cheated you guys. There is in fact that middle step. You got me. Thank you. Much appreciated. So, but yeah, any number is smaller than its absolute value. Exactly. That's equality when a dot b is positive, and it's something interesting when a dot b is negative. So then what? Well, these are both non-negative quantities, so we can take the square root of this inequality, and that implies that the magnitude of a dot b, a plus b rather, is less than or equal to magnitude of a plus the magnitude of b. Now the reason this is called the triangle inequality is easy enough to illustrate, right? If you draw the vectors tip to tail, what do they look like? Try a triangle, right? You have to use your imagination a little bit, but here's A, right? Here's B. So the resultant of A plus B, right, is this guy. So what this inequality is saying is that the length of this is smaller than the length of this plus the length of that.
So it's kind of a mathematical way of saying the shortest path between 2 points is a straight line.
Yeah.
Question. Could you have also done that proof by stating that unless the two vectors were collinear, they would form a triangle with the resultant, and since the two sides of a triangle are always greater in sum than the
So your question is, could you prove this with geometry?
Yes.
And
which wouldn't require you to resort to number thinking.
well, I don't know. That depends on your courage to visualize triangles in n dimensions.
Well, assuming they're still triangles, then presumably it could be extrapolated.
So you're saying in n dimensions there exists some plane on which the vectors lie, and I can do
Yes.
two-dimensional coordinate geometry in said plane. Yeah, I think that's reasonable. We always have this interplay. Do you do algebra or do you do geometry?
Well, I mean, they're
I'm not
both
saying one
math
is-
and they're both
I'm not saying-
related.
Right, but to those who are more algebraically inclined, this proof, of course, is very satisfying because it's complete. Like you can't, there's no visualize this step, right? In every geometric proof, there's some kind of imagine such and so forth, right? And depending on your geometric inclination, you may or may not find that useful. But yes, it's often the case once you understand geometrically what's being asked, the geometric proof is much simpler. I'm not opposed to geometric thinking in here. In fact, I'll require it. So, yeah.
Well, you're going to have to in a few chapters.
Yeah, exactly. So, Cauchy-Schwarz. Cauchy-Schwarz, I'll show you. So here I have a sneaky little argument I'll share with you that I found 2 years ago. So here's how it goes. 0 less than or equal to the norm of, well, let me just a second here. You guys have been patient with me thus far, but I'm going to use the projector for Cauchy-Schwarz, if you don't mind. Because I do want to actually get to some more calculations here, and if I do this proof by hand, it'll eat 10 minutes. I only want it to eat 2. So how are your classes going?
Well, haven't even had some.
Haven't even had some of them yet. Yeah, I'm still on the fence. I might pick up another class today. It kind of depends on, like, we've got bonus students from applied linear algebra, so either Dr. Smith or I will teach another section of it, possibly if it gets to 10, you know. So like right now we're competing between 3 different time slots. So I was winning last time, but I still don't have 10 students. So.
Does the winner not teach it, or does the winner teach it?
Oh, the winner. I'm just talking about winner teaches it, but yeah. I mean, I don't really need to teach it, so it's just because I, I pity the students that don't have a class to take, you know. But so the argument's a little bit. No, there's another popular argument you'll find if you look in books and stuff. So this is a little bit to like a mathematician who happens to be watching this for some unknown reason. There, of course, is a standard argument, which I'm not giving here. But I like this argument because it showcases the use of unit vectors. So suppose you've got, first of all, the Cauchy-Schwarz inequality is clearly true if either one of your vectors is 0, all right? So like, we can assume that the vectors are non-zero, right? And if the vectors are non-zero, then that means we can define the unit vectors, x hat and y hat, right? We take x over the length of x, y over the length of x. These define x hat and y hat. All right? So what's x dot x? X hat dot x hat, well, that's, if you look at that, it's x dot x over the length of x squared. But what is x dot x? X dot x is the length of x squared, right? So x hat dot x hat is 1. This isn't surprising, right? X hat is a unit vector, so the square of its length should be 1 squared, which is 1. So I'm just saying it's aptly labeled. All right? And likewise, y dot y is 1. So if we consider 0 is less than this, I think we can all agree that that's a specific vector, right? So its norm squared is non-negative. Then you expand the dot products. So we've got x hat dot x hat plus y hat. This is 1, this is 1. That's 2. There's 2 of these, right? So we get minus 2 is less than or equal to plus or minus 2x hat dot y hat. Move the minus to the other side. So what I have is that plus or minus x hat dot y hat is less than or equal to 1, which shows you what? X hat dot y hat is less than or equal to 1 in absolute value. There you go. Well, that's not quite it. Then you go back, back up to, well, let me just go to the next slide. So then to complete the argument, since this is less than 1, x dot y is length of x times x hat, length of y times y hat. And so I can pull these numbers out, but this is less than or equal to 1. And so there it is. This is the Cauchy-Schwarz inequality.
It's a lot of bars.
It is a lot of bars. It's probably a little bit dangerous of an argument to give here at Liberty, but it's okay. You guys allowed to go to bars now? No? Just I don't know where we are. I'm just checking.
I suppose you could if you're passing out tracts and not ordering.
If they play CCM, is it allowed? I don't know. Let's see here. So all right. Sometimes I skip over these proofs when I teach this course, but I think it's actually important for us to take a minute and prove these things, because we'll be using dot products and vectors and lengths of vectors throughout the rest of the course, and it's important for us to understand the foundations of where these things are laid. And it's really just simple algebra, right? Now, this Cauchy-Schwarz inequality that I've just shown you the proof of is so important because it allows us to define angle measure, all right? Let me show you what I mean. So consider this then. So if A and B are not equal to 0, then A dot B, right, the magnitude of that, is less than or equal to AB, right, where I finally remembered that I should use my notation. Okay, honestly, folks, it's not an accident that I use the double bar notation. I use the double bar notation in these proofs to draw attention to the fact that I'm making a distinction between the vector and the number, right? But at some point that gets old. The notation gets very tiresome, so it's much nicer to use this drop the vector notation for magnitude, okay? All right. I know if I ask you the question, which would you rather write on the test, this 30 times or that 30 times, I know which one you'll choose, right? You're like, well, why don't I just write A all the time, and you decide which one's the vector and which one's the scalar, and just assume I'm right. See, this is what I won't do. If I see you write a scalar where you should write a vector, that makes my grading easier. but not in a good way. Please don't give me your points. I have enough already. So check this out. If A and B are non-zero, then what? A is not equal to 0, and B is not equal to 0, right? So that means that the norm of A, excuse me, the absolute value of A dot B over AB, right? And we can put the absolute value bars around the whole thing, right? Because A and B are positive. So this is less than or equal to 1. So what that means is we can find a theta such that A dot B over AB is equal to cosine of theta. And in fact, you can work out that geometrically that is, in fact, the angle between the vectors A and B. You can apply the law of cosines in the plane which contains the vectors A and B, and in so doing, you can derive this relation as well. I won't do that in here. That would eat 30 minutes. So anyway, here's the picture. You'll just have to trust me about that. Here's A, here's B. This is the angle between them, theta. More to the point, here's the take-home message. A dot B equals to A, B, cosine theta. Now, I think I have some more derivation in the notes. I'm a little rusty. I might even have that in notes. Let me just scan through here. I forget if I cut it out or not. Let's go on. All right, so another way to look at this, of course, is what? Theta is equal to what? Cosine inverse of what? Solve this for theta. What do you got? Right. Very nice, right? So we can go back here and find the angles between the vectors we calculated the dot products of, right? Let's take a minute to do that. Let's go back to our example 1 and example 2. Find the angles between these vectors.
Does A dot B over AB always give a value in the domain of the inverse cosine function?
Yes, because Cauchy-Schwarz inequality. So the length of V is what? The length of W is what? Square root 5, right? And 5. Ha! Cool. 9 plus 16 is 25. Square root of 25 is 5, right? That's funny. So theta will be inverse cosine of what? Inverse cosine of V dot W over VW, which is inverse cosine of, let's see here, dot product was 11 over 5 root 5. Whatever that is. I'm sorry, have I written where you guys can't see? Oh, my laptop. There we go. Aw, man. So I went to this math conference over break for like 4 days. I was sick 2 of them, so really only 2 days. But I took my calculator out of my computer bag to save weight for some reason. So I don't have a calculator on me. Anybody have a calculator handy? Could you find what that is, inverse cosine of that? I would like it in degrees. I mean, we work in radians here because, as you know, radian calculus is like nice, but personally, visualization for me happens in degrees. I don't know, I just don't see things in radians personally. I don't know about you. While he's doing that, how about this one?
Um, 10.33.
10.33, approximately, of course.
Well, actually, 10.305.
3-1 there. All right, so does that make sense geometrically here? What's going on? We've got 1 up, 2 over, let's see, rather 1 over, 2 up. So here's V, right? Where's W? It's 3 up. So it's like here. So by my rough, sketch here on the board, that makes sense, right? About 10.31 degrees. Of course, given graph paper and enough, you caring, maybe somebody pays you $1 or something, you could figure this out, right, with trigonometry. But my point is we don't have to do that because we have a dot product. Don't have to draw a picture at all, right? It's algebra. Here, what do we got? Oh, this one I don't need a calculator for. This is cosine inverse of 0, right? Here, A happens to be root 2, and B happens to be root 3, but who cares, The length of A, the length of B, right? But that 0 over square root of 6 is still 0. So inverse cosine of 0 is 90 degrees, right? Now here, it's a little bit harder to visualize, right? I can still hazard a picture. Try. I know we're all limited in our ability to draw these kinds of pictures, but that doesn't mean we should give up on them entirely, especially not in this class, yes. So here's A, roughly speaking, and
You should switch to X and Y.
yeah, it's too late. It's back here, basically. And it's a right angle, so anyway. So the y and the z are positive, and it's behind the yz axis. Admittedly, these kinds of pictures are, sometimes open to interpretation, right?
They're fundamentally ambiguous because they're projections.
Exactly. Yes, projections lose information. Okay, so another question, follow-up question. If you think about a cube, right? What is the angle between any vertical leg in the cube and a diagonal between that point? So like, say what's the angle between this diagonal and this leg here? "45 degrees. Thank you. Thank you. I've never disappointed my students to give me that answer, because that's intuitively what you think, right?
But it won't be.
That's right. That is actually a rectangle.
Yeah.
But let's derive this with dot products, okay? So what we're going to do, let me show you why that's not 45 degrees, okay? The short answer is if you look at this slice, this length is not the same as that length. So it's not a square. The diagonal cross-section of the cube is not a square, and that's why it's not 45. But what angle is it? Let's derive it with dot products. So if we put this as the origin, right? And it doesn't matter if this cube is a unit cube or a cube of side length L, right? So don't feel bad. I ask this question every time I teach physics, every time I teach calculus 3. There is always the majority opinion in the class of 45 degrees. It is pretty much universal. The only thing that can poison this is if people have had a class with me before where I've already done an example. So anyway, let's see here. So 0, 0, 1. B, on the other hand, 1, 1, 1 if we use the unit cube.
The dot product's just 1.
Right, so A dot B is what? Yeah. And how about A? A is 1. What's B? The magnitude of B is root 3, right? So this theta should be inverse cosine of 1 over root 3, which is obviously 54.1 degrees, give or take. Am I wrong? See, this is very annoying to me because I think I know this correctly, and yet probably if I was pushed, I might not know the birthday of some of my children. So you can't derive those dates. You just have to remember them. I love my children, but you know, I don't love trivia. Let's see here. Fortunately, my wife does not watch these videos. Let's see here. I think we're okay. All right. So I think what I'm trying to get across to you is if I ask you to find the angle between two vectors, do I want you to draw a picture and try to visualize it? No, I do not. Right? I mean, there is a place later where we need to visualize vectors as they relate to surfaces and things, all right? I'm not saying it's completely off the table, but for these kinds of problems, the right tool for the job is the dot product. Okay? Let's try to work a harder problem, all right? So I wanted to devote a few minutes of class here to try to work a harder problem. Then we'll get back to other interesting uses of the dot product. So the harder problem I thought we might try to work together is the tetrahedron. So here's the reason I was late for class. It took me like 5 minutes to put this together. So what I want to know is what's the angle between any two legs? Now some of you have had organic chemistry or something, right? So you already know this because it was told to you. What's the angle?
60 degrees.
No, I think we're thinking about the wrong pair of legs. You're right, it's 60 there. Curses. I guess I'm asking for a different angle. I want to know the angle. Aw, man. Didn't get enough tape here. Yeah.
Are you looking for the angle between the vector that would be drawn from the center of the tetrahedron to any two vertices?
Yeah, I think that's the one I'm looking for. So like, aw, man. So if you drop a vertical down, what's the angle between that vertical and, yeah. So what's the angle between the vertical and the up off the base, I guess, is the one I'm looking for, yeah. Let me hazard a picture of that. I had these stupid rubber bands. It was going to all be, I should use string. Oh well. I found rubber bands, didn't find string. Ah, man, my yo-yo's got string. Curses. So I asked Dr. Wang, I was like, Dr. Wang, do you have a tetrahedron? He's like, a what? I was like, you take 4 equilateral triangles, you put them together. He's like, oh, no. But then he come running after me. He's like, markers, use markers. And tape. I'm like, oh, okay, yes. I've got those things in my office. So I like this example because it's going to give me a chance to expose you to the idea of the centroid also. So let's we need, to make use of the coordinate geometry, let's just put 2 of the vertices of the tetrahedron on the x-axis, all right? Right? So that puts the other one out here somewhere, right? So I'm saying that this is the bottom face of the tetrahedron. I'm gluing one of the legs along the x-axis, right? So if the x-axis is pointing out at you, basically I'm putting it out like this, but of course I have to draw it like that. So this, if the x-axis is pointing out at you, I'm putting this leg along the x-axis, and that puts this lower point somewhere in the xy plane, right? So that this point is that point. Then the thing that's hard to draw, and will take us a little bit of thinking, is, and I'll abuse, like this picture is, you make what you want of it. Oh, let me try to at least be straight. So then there's, curses. I don't know. I'm never happy with these pictures. Let me pick up poison. Dagnabbit. Everywhere I draw it, I don't like it. I'm going to use a different color for the other leg. For some reason, it'll make me feel better. See, that's just, I don't want these to be so close together. Stink. Why did I agree to do this problem in class? What am I doing? Let's see here.
Just your x-axis, it'll make it look better.
Yeah. It's just going to look bad. All right. So all right. Anyway, sadness of my picture aside, that's why I brought the thing in, because I knew this would happen. Some of these points are easy enough to label, right? This is 0, 0, 0. And this point right here, we can understand as 1, 0, 0, right? This point out here, we can figure out with trigonometry, right? Now, the sad part about my picture is the projection of the vertex, the top point there, right? Let me call it V. What's the projection of V? So the projection onto the xy plane of the point V is just what? Let me call it P, just to give it a label, right? So it's sad, sad picture. That is supposed to be a vertical line, guys. Okay, so understand that my picture is somewhat heuristic. But the picture will give us a guide to the calculation, all right? So first of all, how do we figure out, let me call this point Q. How do we figure out this point Q in the xy plane? Well, first of all, it's in the xy plane. I chose to put that face of the tetrahedron in the xy plane, right? I chose coordinates to make our life easy. So I already know that 0 is over here, right? And I also know by symmetry that it's halfway out to 1, 0, 0, right? Along the x-axis. Like if I take the projection of Q, the projection of Q onto the, let's say, x-axis, it's pretty clear that that is, what, 1/2? 0, 0. Now I'm using this projection geometrically at the moment. I will give you definitions for the projection algebraically after this example. Okay? But I think this example is useful to help you understand the importance of projections to actually solving somewhat complicated problems. Projections are huge. So that's the shadow of Q onto the x-axis. The closest point on the x-axis is that midpoint. All right, so geometrically then it's pretty clear that the x-coordinate of this is 1/2, right?
And if you draw the line through P and Q, then you find you have a 30-60-90 triangle. So by memorization, the y coordinate will be square root of 2.
Right. So here I'm gonna take another. Sometimes it's very helpful to just kind of focus on a particular triangle in this three-dimensional shape and use just plain old right triangle trigonometry there. So here I have the origin. This point is Q, right? This is that projection. This is that 1/2. And we can see that, like you just said, it's a 30. Which one is 30? Is that one 30? This one's 60, right?
So the left is 1, like 1/2, and then the hypotenuse is the first one.
So this is 1/2. What's this then?
Square root of 3 over 2.
Square root of 3 over 2? So in other words, this is square root of 3 over 2. If you look at that triangle there, right? Now, if you don't know special triangles, of course, you can get out your calculator, do trigonometry, figure that out. All right. All right. So now we know the origin, we know 1, 0, 0, we know Q, right? So I don't think I have clearly enough stated for you what the problem is. The problem is we're trying to find the angle off the base face of the tetrahedron up to one of the legs. So what I'm trying to figure out right now, guys, is the angle. I mean, admittedly, I didn't state the problem, right? But we've been just sort of exploring this shape, trying to understand data about it piece by piece. But what we're after, guys, is the angle between, I'm going to draw it here, but I won't calculate it here probably. I guess I might, I don't know. So this angle, what's this angle here is our question. So I'm talking about the angle off the face of the tetrahedron up to one of the legs. It's not 60 degrees. For much the same reason as it wasn't 45 degrees. That slice is not an equilateral triangle.
But it's less than 60 degrees,
Yeah.
right? No.
Yeah, it will be less than.
No, it'll be more.
Less.
No, it is.
Anyway, what is...
Because the 60-degree angle between any two faces is on the slant. So if you were to take that 60-degree angle and just sort of drop it, it would go dip below
See,
the surface plane.
this is what always happens. After I get a little bit into a problem, those who have geometric intuition will start to see the end of it, right? But you have to wonder, I don't know, I can't judge it. Like, I have put a question like this. Here's the variant I usually put. Find the height of the tetrahedron. I put this on more than one Calc 3 final. Usually students can't answer it. It's a simple question, right? What's the height of the tetrahedron? How high is this? Off the table, right? That's a genuinely three-dimensional problem is the thing. So here's my approach anyway. So I'm just trying to find this angle, which is about the same question. How do you find that point P in the middle? This is where the idea of a centroid comes in. So what you want to find is the geometric center of these 3 points. So the way to do that is P is just equal to 1/3 of the sum of the points. So you just take the sum of these. You take 0, 0, 0, plus 1, 0, 0, plus this one that we had to do some work to figure out, 1/2 √3/2, 0, right? And this will tell me the coordinates of P. So P, in fact, is equal to 1/3 of 3/2 √3/2, 0, which of course you could also write as 1/6 of 3 √3, 0. Now that we know the coordinates of P, it's an easy matter to figure out what that angle is, right? You could also visualize the angle back here, right? Right, we could see theta in here. So I need like another color marker. I don't know if I'm. No! I lived a good life. Ow. Good thing I'm not teaching 2 sections of Calc 3. Let's see here. So this angle here is what I want. The angle between this guy and that guy, right? So this is this, right? That's the P vector. Aw, man. Oh.
Does that mean you have to find the height?
Oh. I thought I was ready to do it. Yeah, I gotta find the stupid height. Dang it. Do I have enough information? I know the length of V though, right?
Yeah.
But the problem is, to,
Nah, I need it. Yeah.
if you just wanted to find the, because any vector can be found from the magnitude and the direction, but to have the direction, you need the angle. So you actually have to do a lot more geometry to get it.
Yeah, I need more information about V anyway is the point. So how do we figure out more information about V? Ideas?
I've been working on that one.
This much we can say. What is the, I mean, I have information about V. V is equal to, the thing we don't know, right? Well, what we do know about V is it's at, 1/2, I'll write it as 3/6, and then √3/6, right? In other words, this is also, well, the projection of V is P, right?